Now, draw the shear force. Draw the shear force and bending moment diagram. Draw the shear force and bending moment diagram for the beam below. For the beam below. Indicating all critical values. Indicating all critical values. Indicating all critical values. Alright, so let's solve this please. This is a sample example question, just like this. So I just brought in two new concepts, and that's what's called the critical value. So I'll explain or dwell more on the concept of critical values, right? But it comes to drawing shear force and bending moment diagram for this. We've done something like this before. There shouldn't be a problem. But let's just go through this. We'll draw shear force and bending moment. They will now do critical values. See how we work on critical values, and that will be this. Alright, so if you observe this beam here, for this beam, I've already drawn the free body diagram already. Right? There are no support system. I've already drawn the diagrams. Alright, so here's my free body diagram. There's an arrow A here, there's arrow B here. And we said our first concept before that. If I look at this here, there are four forces acting on this system. There are four. I have arrow A, a point load, 50, a point load coming downwards. I have 30 kilograms per meter, which is a UDL, and then arrow B going upwards. So I'm having 3 point loads, arrow A, 50, and arrow B, and I have 1 UDL, that's 30 kilograms per meter. So how do we solve this? Our first concept is we'll take the summation of vertical forces is equal to 0. So we're saying sigma sum Fy, force in the y direction, that's vertical force, being equal to 0. We're saying if you're going upwards, take it as positive. So I'm having this here. So what does it mean here? RA is going upwards, becomes positive. So I'm having RA. Next up, I have 50 coming downwards, becomes negative, becomes minus 50, of course in kilonewton. Next up, UDL is coming downwards. Convert UDL to point load. How? Multiply the UDL by the UDL distance. It becomes minus, the UDL is 30. The UDL distance here is this, that's 4, plus this, that's 7. So 7 in total, 2 and 2, 4, plus 3, 7. So it becomes 7. Then finally I have RB going upwards, so it becomes plus RB is equal to 0. That's all. This now becomes RA minus 50 minus, this gives you 210 plus RB is equal to 0. Work on these two now. I have that RA minus 260 plus RB is equal to 0. Move this over here. I have RA plus RB is equal to 260 kilonewton. That's my first equation. Next up, I'm having two unknowns. The concept is eliminate one unknown, of course, by using the idea of taking moment. So take moment about one of the unknowns so that it will eliminate that one, leaving you with just the value of the other unknown. Now I said in a case where I have a beam where one support is at the extreme and one is in between the beam, I said please, to make it easy for you, always take moment about what there, the one at the extreme. The one at the extreme. So in a second example, look at where both of them are actually inside. How is that one there? But for now, let's take moment about the one at the extreme. So I'll take moment about this point. Of course, if here's arrow A, this point is A. So I'll say taking moment about from the conditions of static equilibrium. We said the sum of the moment about A is equal to 0. Trying to indicate direction, I'll say if it's going this way, that's clockwise, becomes what there? Positive. Alright, so here's my A. Now, aside on this point A here, I have arrow A. And we said arrow A, of course, will not be considered because the distance is 0. So arrow is up. So I'm left with just 3 forces. That's the point load here, 50, the UDL here, 30 kilos per meter, and then RB. So I'm moving all of these forces to this point. This 50 is coming down this way. That's what there, a clockwise motion. Because it's coming down like this to discuss. So this becomes clockwise motion. So it becomes 50 positive times distance from 50 to here, 2 meters. So I'm having 2. I'm done with 50. Next I'll take UDL. UDL, as you can see, is coming down. So down this way becomes this motion. Down to A. Down to A like that's also what there. A clockwise motion. It becomes plus. For UDL there, your first concept is to convert the UDL to what there? A point load. How do you do that? Multiply the UDL by the UDL distance, 7. This is now the force. Next up, get distance. We said it has about there, half of UDL distance. That was the hypothesis there. Right? My distance here is 7. It will act as half of this, so because what there? Half of what there? 7. So I have this. So I work with this and this. Finally, I have RB. RB is going up this way. So here's my direction of motion. That becomes anti-clockwise. It becomes minus RB. We get distance between RB and here. That's what there? 4 meters. It becomes minus this into 4 is equal to 0. Work on this now. What do I have here? This gives you 100 plus 210 plus 3.5 minus 4RB is equal to 0. Alright, so this gives you 100 plus, which value is 735 minus 4RB equal to 0. Work on these two. I'm having 835 next up minus 4RB is equal to 0. Move this over here. I'm having minus 4RB is equal to, this one comes and becomes minus 835. Of course, get RB is divided by minus 4, divided by minus 4. This will cancel this. So RB is equal to this new value 208.75 in what there? Kilonewton. So let's get RB there. I'll now put RB, put the value of RB into equation 1. That's this. From 1 I have that RA plus RB. RB is this. That's 208.75, okay, is equal to 260. Right. So move some over here, of course. So I'll have that RA is equal to 260 minus 208.75. Please give me value. 51.25 kilonewtons. So I've got the value of RA and RB. That's all. Your next task now is to do your shear force calculation. Let's see shear force calculation. Let's see shear force calculation. When it comes to shear force calculations, your first task is to pick out the correct intervals. Please, In this question, please, which interval do I pick here? I'll pick this one here. Where else? At this point, Abi. Where next? At this point here. Is that all? Here. So here's the task, please. If you're picking intervals, you will always pick interval at the beginning and the end. Very constant. You must pick those two. So of course, these two must be there. So apart from these two again, where else can you pick? I said pick at the point loads. I'm having a point load here, so I must pick here. Why? I'm expecting two conditions. Also, I'll pick at here again. It's a point load. Why? There are two conditions. This one is a UDL, so you can leave it if you want to. If you want to stay, you can say at X point, this is 7. The beam is 7. You can say at X equal to 1, 2, 3, 4, 5, 6, 7. It's possible, but it's time wasting. You don't have that time. To make it easy for you, just pick 1, 2, 3, 4, and that's all. So starting from here now, at X equal to 0. So at X equal to 0. So we said the idea of shear force is very simple, right? What's the idea there? If the force is going upwards, should be what there? Positive, that's all. So at X equal to 0, that's the beginning of this beam here. At this point, now what do you see? I can only see arrow A going upwards, so it becomes positive. So I have just arrow A going upwards, becoming positive. So I have arrow A, and the value of arrow A is what? 51.25 in kilonewton. My next point will be at X equal to where I have a point load. That's here. So that's 2 meters. So at X equal to 2 meters. We said when you have a point load, there should be two conditions. So I'll now have two conditions. Alright. Condition 1, we said shear force is equal to all the forces before that point. All the forces before that point. So here's my point here. Before this point, I have just two forces. This one going upwards, and of course, UDL here coming downwards. At X equal to 2, that's here. Please, you don't consider this one here. Just this one. Two forces, this going upwards, this coming downwards. Alright, so first of all, this one is going upwards, becomes RA. Positive, it becomes RA. Next up, before this point here, I can see UDL here is coming downwards. Now at this point there, if you look at this, all of these are still UDLs. Now the distance here is 2. So convert or what we just this UDL here, because we said to convert UDL to point load, multiply the UDL by the UDL distance. For this distance here, I'm having just 2 meters. So because the UDL there, 30 times this distance there, 2. Now since it's coming out, because what there? Negative. So it becomes minus 30 times 2. So I'm having minus 30 times 2. This is before that one there. So this now gives you equal to RA is 51.25 minus 60. What's your value, please? Minus what? Minus
8.75.
8.75 kilonewton. I'm done with this. Condition 2, we said shear force is equal to all the forces before that point, which is usually a repetition of condition 1, which is RA minus 30 times 2. So this was condition 1 there. All the forces before this point, that was this and this. Next up, plus the force at that point. At this point, you can see 50 there, it's coming what there? Downwards. So it becomes what? Negative. It becomes minus 50. At 2 meters, I have 50 coming downwards, so it becomes negative. So having this is equal to RA is 51.25 minus 60 minus 50. Please give me this value. Minus 58.75 kilograms. Alright, let's proceed. So we're done with two conditions at this point. Next up, this point next, at x equal to 4 meters. So at x equal to 4 meters. Obviously, there will be what there? Two conditions. the point load there, to condition. Condition 1, we said shear force is equal to all the forces before that point. Now, here's my point. Look at the desk, please. Before this point, how many forces do you see there? 3. RE going upwards, this coming downwards, and then UBL. If it's going upward, it should be positive. So RE going upward becomes positive. I'm having positive RE. Next up, I can see 50 coming downwards, so it becomes negative 50. Next up, I can see CUBL here. It's coming downwards, so it becomes negative. Your concept will now be convert the UBL to point load. So multiply the UBL by its distance. In this case now, I'm considering distance as what there? 4. It becomes what there? 30 times 4. That's all. It becomes 30 times 4. In cube values, R is about 51.25 minus 50 minus 120. Please give me value. Sorry? Minus 118.75 in kilonewton. Alright, condition 2, we said shear force is equal to, in a brief, is equal to condition 1. Just simply repeat condition 1. That gives you RA minus 50 minus 30 times 4. Next up, plus the force at that point. Here is X equal to 4. That's this point here. At this point, I can see RB. RB is going upward, so it becomes what there? Positive. That's all. I'm now having positive RB. So always observe. Condition 2 is always equal to condition 1 repeated, then check for the force at that point. Right? Condition 2 is always condition 1 repeated, then check for the force at that point. That's all. In cube values here, it becomes RA, that's 51.52.25 minus 50 minus 120 plus RB. Please read the value of RB. 208.75. Please do this math. What do you have? Sorry? 90 kilonewton. Alright, one last one, that's here. It becomes at x equal to 7 meter. 7. 2, 4, 7. Please, just go to 7, please. Would there be a condition there? No. No. Why? There is no point load here. What you see is a UDL. There's no point load. So what there? No two conditions. Alright, if there's no two conditions now, work on this. What do you have here now? I will have that the shear force is equal to, just take normal shear force, since there's no two conditions. So what do I have there now? I have RE going upwards, becomes RE being positive. I have 50 coming downwards, that means 50 negative for coming downward. I have RB going upwards, becomes positive RB. I have UDL coming downwards, it becomes negative. Your task is convert the UDL to point load. That means multiply the UDL by the distance. In this case, I'm considering 7 meters, so it becomes 30 times 7. I'm having 30 times 7. So this will give you 51.52.25 minus 50 plus RB. RB is 208.75. Then next up, minus 210. This gives you what there? 0. Study 100 times. Shear force will always end with 0. Always end with 0. So it's easy. let's do bending moment calculation. So we say for bending moment, you still take intervals. I'm using the exact intervals. I use the word there, shear force. My shear is like 2, 0, 2, 4, and 7. Use the exact interval. So case 1, at x equal to 0, I said don't stress. Don't stress. Bending moment is what there? 0. Don't stress. 0. Next up, at x equal to 2 meters. My bending moment is equal to, now hang on, here is 2 meters, this point here, right, from here to here is 2 meters. So the case is this, for moments we're looking at clockwise motion and anti-clockwise motion. So here's my 2 meters here, this force is going upwards like this to this point, right, up to this point. That becomes for there, a clockwise motion. Moment is force times distance, so since it's clockwise, it becomes positive. Becomes force RA times distance, that's 2. So I'm having here as equal to RA times 2 in K. Your first task is to convert UDL to point load. So it becomes, my distance here is 2. Convert UDL to point load. So it becomes 30 times 2. 30 times 2. Next up, distance. Distance becomes what there? Half of the length. My length is 2, so it becomes half of 2. Right? Half of the length. That becomes half of 2. In cube value, I'm having 51.25 times 2 minus 60 into half of 2 is 1. So this will now give you equals what there? 102.5 minus 60. Please give me value. What do you have? 42.5 kilonewton meter. Okay? Let's get this done. At x equal to 4 meters, that's here. My bending moment is equal to clockwise RA times distance 4. Next up, you can see this one here. Coming this way, that becomes what there? Anti-clockwise minus 50 times distance from 50 to this point here. That's 2. So I'm having 2. Next up, you can see UDL there. So of course, it's coming downward like this. That becomes anti-clockwise. So minus, convert UDL to point load, multiply UDL 30 times, for this case here, distance considered is 4. So times 4. This is the force. You said it acts as what there? Half of the length. The length is 4. It becomes half times 4. This now becomes 51.25 times 4 minus 100 minus 120 into half of 4 is 2. So what do we get here? 2005 minus 100 minus 240. Please give me this value. Minus what? Minus 135 kilonewton meter. One final one at x equals to 7 meters. Okay, so at x equals to 7 meters, at x equals to 7 meters, please take bending moment. My bending moment is equal to, so 7 is this point here. Take all the force to here. Now, first of all, I'm having RA going upwards this way. So here's the motion, becomes clockwise. So I'm having clockwise RA times distance from RA to here. That's 7. Next up, I have 50 coming downward to this point, like this, anti-clockwise. So minus 50 times the distance here, from here to here, that's 5. Next, if I have RB going upwards this way, so here's the motion, that's what there, clockwise, becomes plus RB, get distance of RB, that's what there, 3, I'm done with this. Finally, consider the UDL. UDL is coming downwards to this point, so it becomes this motion, that's anti-clockwise, so it's negative. First of all, convert UDL to quantum, multiply the UDL 30 times UDL distance here, 7. Next up, this is now the first. We said for distance, it will act as what there? Half of the total length considered, that's 7. Alright, in field value, this is now equal to 51.25. That's RA times 7 minus 50 times 5. That should be about 250. That's 250 in value plus ROB is 208.75. So ROB times 3, that's times 3 here, minus 30 times 7 is 210 into half of 7 is 3.5. Please punch all of this. What do you get? Punch all of this. What do you get? Like punch all of this gives 0. So our rule still applies. Bending moment starts with 0 and ends with 0. Our rule still applies. So that's it. Let's draw the shear force and the bending moment diagram. This was 50 kilonewton. Here was RB. Please give me RB's value again.
RB is 208.75.
Okay. Give me RB's value again.
51.25.
We have 30 kilonewton per liter ranging this way. So I said take intervals at where you have or draw straight lines where you took intervals. Those are these points. I took at this point. So this was an x equal to 2 meters. Here was 2 meters. That's 4. And here was 3 meters. And that's this. Of course, the end of the beam. Alright, so let me clear you up. So look at me. I said take moment about this point here. Now what if I was to so here's where you mix it up. Look up. Now listen. What if I was to take moment about B? Here. Let's assume I think about B. I will think about B. What do you do? Look up. It becomes technical. I'll take movement both from the left and the right. That's unusual, but that's how you do it. So here's my big one, this point here. Take movement from left and right. Start with left. If I go with left here, at the left I have 3 forces there. UDL, point load. Let's draw shear force and bending moment diagram. Please check. For bending moment, do I have negative values? Check. I have negative value. So what does it mean? It means to slope downwards. So hence, raise the datum. So I will draw the datum somewhere upwards, somewhere here. If you check previous example, we used to draw that in here. Why? We had just positive answer, so to go upward only. In this case, I'm having negative value. That means the bending moment diagram got there to slope downwards. So catch that with up. Somewhere around, let's say here. Let's draw here. Alright, shear force somewhere around here. Please check shear force value, please. What's your highest shear force value? No, the highest positive value. What's the highest positive? Okay. What's the lowest negative value? Like the lowest? Alright, so that means this is the highest. I'll take here. The highest shear force is 90?
Yes.
Okay. So I'm having somewhere here. I'll call here. They said at x equal to 0 here, my shear force is about 51.25 kilonewton. That's this. At x equal to 2, we had two conditions. Please check condition 1. What's the value? So look at this. Minus 8 means 8 on the negative region, I mean? Yeah. So I'll take somewhere here as being 8 point what? 75 kilonewton. That was condition 1. Condition 2 became what there? So this same point here, that's what I'm saying, two conditions. Condition 1 is 8.75, condition 2 is 58.75. That should be still below. Minus 58, that's 58 downwards. So somewhere here, 50, let's assume here is 58. So here gives you about, here gives you 58.75 kilonewton. So I'm done with this. Now check at x equal to 4 meters. I have two conditions. Please check what's condition 1. So somewhere around here, I have 118.75 kilonewton. I have this. Alright, that was condition 1. Condition 2 was what? 90. So look up. I'm drawing 90. My first point here is 51.25. 90 have to do what there? Go above it. So I'll take somewhere above here. Here is 51.25. 90 will be above it. So let's say here, somewhere here, I'll call this 90 for what again?
Just 90.
Just 90. Yes, 90 kilonewton. At x equal to 7. In two conditions, we have what there? 0. So to do what here? To go up a bit. Then what again here? Slant downward. Then go down. From here to here, you do one down. Slant downward. From here, what happens now? Goes up. And what again there? Slant downward. So trace my point. From here, I'll put my first point this way. At every point, put an arrow there. Next up, I'm moving from here to this point. So this one comes down this way. I'll put an arrow head here. From here, second condition, here's my next point. I'll come downwards to this point. From here, my next point here is to go this way, arrow head. From here, upwards again to go this way. From here, 0 to go this way. So, what's next there? Next is this. Next is this. Take up my diagram, that's this. I will take up this one here. If it's above that here, positive. If it's below, because what there? Negative. So shade them. Above, positive. So I'm having this. So this is my shear force diagram. SFD. Shear force diagram. Now let's get bending moment, please. At x equal to 0, what's the value there? Bending moment is 0. At x equal to 2, what's the value there? 2. Yeah, that gives you what there? 42.5 kilonewton meters. Okay. At x equal to 4, what's the value?
Minus 1.5.
That will be down that bit. Okay. Minus 135 only. So it becomes 135 kilonewton meter. Next up, 0. Now look up this. Look up. Look up. Next up now it becomes a bit technical. Look up. Listen. Next up now it becomes a bit technical. Now I said if you're doing shear force for just point loads, use what there? Straight lines. For you there, what is there now? Curves. Become a curve. Now if you're look at it, if I'm doing a curve of this nature, there, somewhere must be my apex point. I must have an apex point in my curve. Where do you expect your apex point in your bending moment diagram? My apex point or my apex minimal occurs at where shear force is what there? 0. If I look at this diagram here, the shear force diagram cuts the shear force cuts this axis at 2 points. Which 2 points? Here's my first point. Look at this. This line here cuts 0 at this point here. So here's my first point where it cuts 0. This one here. Also, this one here, you can see it's not 0. It also cuts 0 at this point. So I have my second point here. That means this one here is the minimum point. And this one becomes what there? Maximum point. So the minimum and maximum point will occur where shear force cuts the x-axis. This shear force cuts x-axis at this point and this point only. Of course, this one becomes what here? Maximum. Hold on. This one here, will it be maximum or minimum? This one here, will it be maximum or minimum? Maximum. Why do you think it will be maximum? Why is it not minimum? Because if I look at my graph, it's going up a bit. Yes, it's going up like this, cuts here and down. So here has to be what there? Maximum. So I will draw it such a way that somehow like this, like this. My apex has to be here. Here will be your highest point, then come down to be a curve, not a straight line. Right? Here comes here. So this is now my apex point. What next is going down like this way, going down like this way. So still a curve. Something of this nature, something like this. It's a curve. Something like this. Okay, what next now? Going to 0. How did I know that here will be my minimum? Why? That's where shear force at 0. Don't forget. I'm having this curve here. Here becomes positive. Here becomes what there? Negative. So this is my bending moment diagram. That's it. Copy down, let's proceed. So this is just halfway solving. Let's now complete it. So this is also find critical value. Let's do it. So this is where we stopped last time. Let's look at critical value. Question. I said the maximum and minimum will occur at where shear force cuts x-axis. Here's my shear force. Where does it cut x-axis? Here. Does it cut it here? No. Just where there? Here. Where else? Does it cut it here? No. Where else again there? Here. So these 2 points become maximum and minimum. That's it. Alright, so next up please. Next up you have to indicate the important points. They call it either important points or what there? Critical values. Let's consider what critical values are. Alright, take out this. Critical values are the most important points in a shear force and bending moment diagram. Critical values are the most important points in a shear force or bending moment diagram. They include number one, position of maximum sometimes and minimum bending moment. That's the first critical value. The second one is called the point of inflection, also known as the point of contraflexion. Alright, so these are like the two most important, right? The position of the maximum and the minimum bending moment, and also the point of inflection, also called point of contraflexion. I'll give you short notes of this and proceed please. Let's explain the first one. Position of maximum bending moment. Position of maximum bending moment. Take that please. This is the point where the value of the bending moment is greatest in bracket for maximum, close the bracket, and least in bracket for minimum, close the bracket, and least, L-E-A-S-T. So simply where the value of the bending moment is what? Greatest and least. So look up it, look up. In this diagram, obviously, here is my maximum bending moment. Here because of there, my minimum bending moment. Take that please. Paragraph. It occurs at the point where the shear force. It occurs at the point where the shear force cuts the x-axis. It occurs at the point where the shear force diagram. It occurs at the point where the shear force diagram cuts the x-axis. Where the shear force diagram cuts the x-axis, I point A, that is where shear force is 0, full stop. It occurs at the point where the shear force diagram cuts the x-axis, I point A, that is where the shear force is 0, full stop. Number 2, point of inflection. What does it mean? This refers to the point where the bending moment diagram. This refers to the point where the bending moment diagram cuts the x-axis. Full stop. That's all. All right. Enough of the theory. Let's see how we can get. Let's have a look at it. So let's find out the position of maximum bending moment. Now listen. When I talk about what I said, position of either maximum or minimum bending moment, right? In your exam, focus on just maximum, right? Just leave the minimum, please. In exam, focus on just what there? Maximum, leave minimum. All right. But of course, if you have time, I can do maximum, and if you have time. But USC here, we work on just maximum. So look at me. How do I get the position of maximum bending moment? You will get it using an idea from GS 3 called similar triangles. That's it. How does similar triangle work? So look up. How does it work? Look at it. So here's the concept. Position of maximum bending moment is here. Right. Traceman up is here. Now, here's what we know. We know that from here to here is how many there? 2. Observe. from here to here is 2. Now observe that the position of maximum bending moment falls before 2. What does it mean? It means that the position of maximum bending moment is what there? Less than 2. Less than 2. So what I need to do is this. I need to find the value from here to here. That's all. Look for this value here. This distance from here to here. Of course, my look at this. Of course, my position of maximum bending moment is here. From here to here. That's the distance. So I need to find this distance. And I'm saying just by focus on this diagram here, you can see that this value should be less than 2. Should be less than 2. So what do I do? If I look at this now, I can pick up 2 triangles. So look at this now, look at this very well, please. If I look at this now, I can see something that looks like this. Something of this nature. This. So you can see this straight line here, this one here. I'll draw my straight line. Okay. What next? You can see this one here, slanting from this point up to this point here. You can see a small triangle here and a big triangle. So something of this nature. But in your work, you make it big, right? Make it big so it's visible. Make it big. So this is the point I'm talking about here. This one here is this point here. Here is positive, here is negative. Now look at this place. This height here is how many? Check. What height here? 51.25. That means this height here is 51.25 in value. Please check this height from the diagram. What do you have? 8.75. So 8.75 kilonewton. Okay? I didn't add kilonewton here. Let me take it out. Just 8.75. So that's it. Alright? 8.75 and then 51.25. So what next? I need to find this distance here. From here to this point becomes the position of maximum bending moment. But how do we get that? That's the question. How do we get that? Look at it. Look at it. From here to here is how many? 2. Alright. We know that from here to this point is 2 meters. Okay. So what next? Let me say I decide to call from here to here as x. From here to here. That means I want to say from the start of the beam to where I have maximum bending moment. Now let me call it x. To here is x. Question is this. Is from here to here is 2 and from here to here is x. What will be the value of this distance here? What do you have there? Is it 2 minus x or x minus 2? Here is 2. Here is x. Here becomes what? 2 minus x or x minus 2? 2 minus x. Becomes 2 minus x. So x minus 2 minus x. That's it. So here becomes 2 minus x. Here's like a layman's concept of this. So I'm having here, this, you see from here to here is about 5 meters. This is 5. Okay. From here to here is about 4 meters. If from here to here is 4, here will become what there? 1 meter. If from here to here is 4, here to here becomes 1. How do you get 1 here? 5 minus 4. So observe this 1 minus this. So 5 minus 4 gives me 1. The same thing, 2 minus x gives you this. It's 2 minus x. So what next here? I will use the concept of similar triangle. So if I look at this, I'm seeing 2 triangles there. My first triangle is this. I'm having a triangle of this nature. We said here is x, this. Here is 51.25. We also have a second triangle like this. We said from here to here is 2 minus x in value. Here becomes 8.75. If two triangles are similar, what does it mean? It means the sides are equal. Or perhaps the ratio of the sides are equal. Here's my hypotenuse, 90 degrees. 90 degrees. Here's my hypotenuse here. So look at this. Here's hypotenuse now. Look at this. If I want to liken them here, My vertical height here is 51.25. So I will say using similar triangles, the vertical height here is 51.25. It should be equal to the vertical height here, 8.75. All over the horizontal height here, x, should be equal to horizontal height here, 2 minus x. That's the concept, that's all. Right? Vertical all over horizontal for this is equal to vertical all over horizontal for this. That's it. What next now? Find x. How? Cross multiply this to this, this to this. Alright, so this times gives you 8.75 times x is equal to this 51.25 into what there? 2 minus x, alright? This to this, this to this. What is that? What do you get here? 8.75x is equal to, what's the value here? 2.5 minus, this one comes in, what do you get there? 51.25 times what there? X. Next time, move this one over here. So 8.75x minus comes here plus 51.25x is equal to 102.5. Sum this up, what do you get?
9.
Hello?
60x.
What do you have? 60x is equal to 102.1 there. 5. Divide there by 60. Divided by 60. So x equal to what there? 1.71 there. It makes sense. It makes sense. This place here, if from here to here is 2. Obviously, here is more than 1, I mean?
Yes.
Because it's more than half distance. You have to be what there? 1 point something. You can see that it's close to 2. Because what there? 1.71 meters. Is that all? No. That's not all. So what next? At this point, now say, therefore, the maximum bending moment occurs at 1.71 meters. Now look at it. If you see 1.71, look up. If you see 1.71 is distance from here to here. Listen, I can look at this point in 2 ways. Either here's a point from here to the left, here's a distance from here to the right. So you're saying at 1.71 meters. Question, is it from my left or from my right? From where? Left. So from please at the left. What was the point there? From point A. That's it. So this was what we call A. It becomes 1.71. You can say 1.71 meters from what? The left. Or perhaps 1.71 from A. That's it. So we've gotten the position of maximum bending moment. So it's 1.71 meters from A. What if I was asked to find the position of minimum bending moment? Don't stress. See minimum bending moment here. So what's the position here? This point, Abi? Exactly this point. What's the distance here? So 3 from what there? Because here is D or C. Or perhaps here is 3, Abi? Yeah. From here there's how many? 4. So therefore, the minimum bending moment occurs at what there? 4 meters from what there? A. It's easy. So this was already exactly here. So you have to strike this. So therefore, the minimum bending moment occurs at what there? 4 meters from A. That's it. So critical point number 2, we said is called the point of inflection or contraflexion. Alright. So look up. What's the point of inflection? I give it is simply the point where the bending moment diagram cuts the x-axis. That's it. So where's that point now? Here. That's the point of inflection. We are bending moment cuts this x-axis. That's inflection. We are asked to find this point from here to here. Now, here's what we know. From here to here is what there? 2 meters. From here to here is 2. From here to here is 4 meters. From my diagram, I can make this inference. My inference is this, that the point of inflection is greater than 2, but less than what there? 4. You can see that. This point is greater than 2, but then less than 4. So my value should be something that is bigger than 2, but less than 4. Alright, so in the case of maximum bending moment, I said use the concept of similar triangles. For this, what do you use? Now, here's the point. I will redraw this now. I'll redraw this. Something about here. You have this going upwards and then here. This one going okay, sorry, let me draw it here to make it clearer. You have this. You have this. So look at this. It goes up and comes this way. So something that goes up this way, somewhere like this. Alright. So here's my point. Look for this point here. Now here's the problem you can see it. You can see this one coming this way like this. From here to here is 2. So somewhere between this point, you have this line coming up here. Somewhere like this. We said from here to here is about 2. Okay, let me call here 2 meters. I'm trying to redraw this diagram in a bigger form. See, it's 2 meters. From here to here, we don't know what this is. I'll call it x. That means from here to this one, I'll call it what there? X, that's it. The same thing, right? Same thing. Call it x. What else can we see? We can see this force here. This was what here? Which force was here? The ROA, yes. So I'll come here, bring back the forces. Yes, ROA. Okay. ROA was what was the value in there? 51.25. What other forces can you see there? From here to here, look at this. From here to here, we have UVL, right? Look at this. We still have UVL here. So my UVL also continues here. This is what I'm doing. So in retrospect, I'm bringing back my forces into the diagram. Yeah, so I still have my UVL here as 30 kilonewton per meter. My UVL was still, or is still here. Hang on. Alright, so bring back the RA, bring back UDL, bring back RA, bring back UDL. Please, from here to here, please check. I brought back the RA, I brought back UDL, please. Can we find the force again there? Check. Look up. I brought back RA, I brought back UDL. Is there the force there? Yes. Which of them there? 50. 50. Please, 50 is acting at what point there? Exactly 2, I mean? Yeah. That means at exactly 2 here, I'm bringing back 50, so I have 50 here. So at this point, I have 50. I have 50 kilonewton. Alright, so that's it. So what? Let's know. Are we good with this? Okay. The concept is bring back the diagram, then replace all the forces. Alright? From here to here is 2. I know so. From here to here is x. I don't know. So I'll call it x. Okay, so what next? Bring back all the forces. I had ROA here, as you can see. Okay, what again there? I had UDL here, as you can see, 30. I also have 50 acting at exactly 2 meters. So at exactly 2 meters here, you can see my 50. And that's it. I'm done doing this. What next? I'm done doing this. What next? Look up now. Now, record something. Record that if I pick moments about any point, it gives me 0. I'll use that idea here. If I think about any point, it's equal to 0. That's not the law of static equilibrium. So I'll simply think about here. Let me call this point. Look at this x. So here's x. So let's say taking moments. Taking moments about this point. Here is the point of inflection. Why is the point of inflection? It's where bending moment causes 0. Think about this point. What do you have? Look up this. Look up. Look up. How do you think about here? What do we do? First of all, look up now. I'm considering this point here. So all the forces are coming to this point. First of all, ROA is coming this way. Please, clockwise or anti-clockwise? So it becomes clockwise. Positive ROA times, please, what distance from here to here? 2 plus x. That's 2 plus x. 2 plus x. Next up, I have 50 coming like this. Clockwise and anti-clockwise. So because what there? Negative. Minus, what's the force here? 50. What's distance? X. Finally, you can see UDL. So because UDL is coming down, so down this way, clockwise or anti-clockwise? Anti-clockwise because what there? Negative. Your first task is convert the UDL to point 2. What do you do now? Multiply UDL 30 times what there? UDL distance. This is what there? 2 plus x. It becomes 2 plus x. This is now the force. Distance becomes what there? Half of the length. I mean, it now becomes what there? Half of what's length there? Half times 2 plus x. So I have this. The halves, let me use this. So observe this thing. Right? Clockwise, ROA times 2 plus x. Anti-clockwise, minus 50 times distance x. Anti-clockwise, minus 30 times this distance here, 2 plus x. Distance becomes half of the length. So half of 2 plus x. Of course, it's equal to what there? 0. So it's equal to 0. What I want to get here now? What's ROA? Into what there? Okay. Minus what here? 50x. Okay. Let's help ourselves, please. Let's expand at once. So we say, okay, I replace this, no problem. Right. So minus what here? Minus this and this. 60. Hold on. This expression is somehow. Don't forget, this is multiplied on this. You have to be careful. It gives you 30 into what there? 2 plus x into, this gives you what there? This gives you 2 plus x over 2. Add it? It's equal to 0. Let's check this out. This times is 2 plus x over 2. Okay? So, if you can solve x here, you're done. That's all. Solve for x here. That's all. Alright, work on this please. This becomes what? This times 2. What do you have there? 102.5. That's this times 2. Next up, this times x gives you what there? Plus 51.25 what there? X. Okay. Next up, minus 50x. Next up, minus 30 times 2 minus 60 minus 30 times x minus 30x. From here, oh, it's not that deep. Sorry. Let's improvise. That's correct, but that's not. That would be bulkier. Let's make it easy, please. I've gotten this now. How to simplify this? These three are multiplied, have you? So what do you do now? 2 here, 1, 2 here, 15. So it becomes what there? Minus 15 into what there? 2 plus x into what again there? 2 plus x equals, you observe this please. Alright? This one can cancel this there. Minus 15 into 2 plus x times 2 plus x equals 0. Solve this question. What do you have here? This gives you 102.5 plus, give me the x's. What do you have here? Huh? 1.25x, this 2 minus 15 into 2 plus x into 2 plus x equal to what there? 0. So expand this to now. I have 102.5 plus 1.25x minus 15 into, if I expand this, what do you get there? 4 plus what there? 4x plus what there? X squared equals what? 0. Have you? 2 times 2, 4. 2 times x, 2x. X times 2, 2x. 2x plus 2x, 4x. X times x, x squared. This is the 1. Having this. Well, then we start doing x plus 2. Is it 2 plus x? 2 plus x into 2 plus x becomes 2 into 2 plus x plus x. No. Please. You pass that level, right? Okay. You have this. Expand this. What do you get here? 102.5. Okay. Plus 1.25x. Use minus 50 to multiply 2. This and this. Minus 60. Minus and this. Minus 60x. Minus and this. Minus 15x squared. All equal to what there? There. Please rearrange this please. Take from the highest value of x to the lowest. This quadratic. So what's the highest here? Minus 15x squared. Okay, what next? Take the x's. I have this and this. So give me 1.25x minus 60x. What do you get? Minus what? 58.75x. Take the constant. Johnson, have it? So okay, no, you got this and this, right? Yeah, so give me 102.5 minus 60. What do you get? Plus 42.1 equal to what there? So I now have the quadratic equation. So just take x squared, take the x together, this one and this one. So this minus this gives you this one, yeah? Take the constant, this one and this one. And have this. To solve this, what's the value of x here? So x is equal to what there? Minus 4.54 or 0. What there? 62. Alright. So which of them is correct? Which of them is wrong? After solving quadratic equation there, one will be correct, one will be wrong. Obviously, x cannot be negative. So x cannot be negative, this one is off. So this becomes the correct value. So therefore, x is equal to what there? 0.62 meters. They say find the position of inflection. So look up now. We said from the beginning of the beam, point of inflection is 2 plus x. We just calculated x, and from our calculation, x is what there? 0.62. So therefore, the point of inflection occurs at, from here to here, 2 plus from here to here, x. Well, x is 0.62, and that's equal to 0.62. That's equal to what there? 2.62 meters. From where there? From A, this point. That's the answer, please. The point of inflection, now because I said it should be a value greater than 2, but what there? Less than 4. That's it. So that's how you solve this one, okay? It becomes 2.62 meters from A. Alright, so that's it. Okay, so at this point now, you'll be wondering how I got these values here, right? So this is a quadratic equation here. So you solve it quadratically using perhaps complete the square method, or perhaps you use formula method, or if you want to, you use the calculator to solve this. But after solving this using perhaps formula method, you have your answers as this and this, right? Alright, so to understand how this is solved, you could check, I did a video on quadratic equations, right? So I'll leave a link in the description of this video, so you can check it out and then see how we solve this, alright? Alright.